C++ has some data structures already pre-built and available within the standard library. We can use these to get familiar with how these structures work from the outside before we worry about how to actually implement them ourselves. But wait, if data structures already exist, why are we going to spend all semester learning how to write them? Well, learning about data structures and algorithm analysis is a big part of computer science. You also need to know the inner workings of these structures, so that when you're implementing solutions, you can choose the best structure for your particular problem. It isn't one size fits all. You might need to create your own data structure down the line, or customize an existing one. And chances are you'll be asked about them during job interviews. Interviewers love asking about data structures. So let's see how some of these structures work by utilizing the structures available in the standard template library. In particular, we will look at the STL Vector, List, Stack, Queue, and Map. Vectors are a linear data structure, and they're implemented behind the scenes with a dynamic array. As a class, it has the functionality to handle certain things for us automatically so that we don't have to. You can access specific items of the vector with the subscript operator, just like you would with an array. A perk of using the vector object is that it handles resizing on its own. Recall that with a static array, we had to know what its size was at compile time, and it couldn't be resized. And with a dynamic array, we had to manually deal with the memory management, and resizing took some work. Because the vector is a class that wraps a dynamic array, when the new items are added to the vector, it will automatically check if its internal array is full, and resize it for us so that we don't have to worry about it. So here's one example of how using a data structure makes a programmer's life easier. To add items to a vector, we can use the pushback function, and it will take care of the rest. So, someone else has already implemented the vector for us, and we don't have to worry about how it works. It just does. A vector can store any data type. The int, string, and float within less than greater than signs are required to tell the vector what data type of array it's going to have, and this all works because it's built as a template. If you haven't covered templates before, or don't quite remember how they work, don't worry, we'll go over them more later on. And if we write a struct or a class, we can even use those in a vector to store a vector of whatever that data type is. Some of the handy functions of a vector are pushback to insert an item to the end of the vector, size to return the amount of items that are in the vector, empty to return a true or false based on whether or not it's empty, the subscript operator so you can get an item at any index in the vector, and the clear function, which will clear out all elements in the vector. So again, vectors are implemented with a dynamic array, which is why we can treat them like arrays. By using a class to wrap around a dynamic array, we can automatically have the structure itself handle resizing whenever space runs out, or handle returning an item whenever the user tries to access something at some index using the subscript operator. C++.com has useful reference pages on all the standard template library structures. You can use these to get more information on the vector and its functions. Let's see how we can use a vector in a really simple program. Okay, let's start off with a simple static array if it's been a while since you've done any programming. So I'm just going to create an array of numbers, let's see, a size 3, so you just put 3 there, and then we can assign values to each of these. And they can be any value. And then we can write a for loop to iterate through all of the elements of the array and display them. So for I starts at 0, and we go up until 3, and go up by 1 each time. We can output the index and the value in the array. So I can build this and run, and it just looks like this. So let's look at the same thing using a vector instead. So we can say vector of ints, and we'll just call this vector numbers. And it might not build right now because we need to make sure to include the vector library in order to use it. And now it builds. And then to add numbers to it, we'll just use the push back function. So vector numbers.push back. And you can keep doing that. And we can also access specific items of the array directly like this, but there has to be something already at that position. If I tried to do this earlier, I do not think that this would work. So if I run this, it should be fine. If I move this up here, it might give me something weird or it might crash. Okay, it gave me a segmentation fault because again, it hasn't inserted item number 0 into the array yet, so it just crashes. But after you have something already inserted with the pushback function, you can reference it directly. So next, let's just iterate through each of these. We'll use a for loop again. Now when we use the size function for a vector, it's going to return an unsigned integer. What this means is it's an integer that is only positive or 0. It can't be negative, and this just kind of extends the amount of integers that you can use on the positive side. So I'm going to write this as unsigned integer I starts at 0, and we will go up through the vector size and up by 1 each time, and we'll again output the item, the index, and then the element itself. So let's also put some labels here, just so we can tell them apart when we're running the program. We'll just say this is array, and let me expand this so you can see all of it. I'll build and run, and we can see here we have 2 3s because I replaced the very first item from 2 to 3, and it just works pretty much the same. You just have to know what the functions for a vector are. STL lists are also a linear data structure, just like vectors, but they are a little different from vectors. For one, you cannot randomly access data with the subscript operator. And to step through a list, you have to start at either the beginning and step through one item at a time in order to the end, or go from the end and go one at a time in order to the beginning. The STL list does contain some handy functions though, like sort and reverse. We cannot randomly access data in a list because it isn't implemented with an array, like a vector is. STL lists use pointers. The list keeps track of what its starting element is, and the ending element, and each element points to the next element in the list. Therefore, unlike an array, the elements are not in contiguous memory slots. This is why it's important to stay familiar with pointers for this class. We will discuss the pointer and memory aspect of lists later on, once we're implementing linked lists. But for now, on to the STL list functionality. Some of the functions of the list that we will explore is pushback to insert an item at the end of the list, size to get the size of the list, empty to get whether or not it's empty, clear to clear it out, sort to sort the elements of the list, and reverse to reverse the order of elements in the list. With a list, we can also use a push front function if we wanted to insert items to the beginning of the list instead of to the end. And again, you can access documentation about the STL list at c++.com. So let's look at an example of how to use a list. So to get started with lists, we'll need to include the list library as well as our normal IO stream. And we're going to have a list of strings, so I'll include the string library also. And we'll just create a list whose type is string, and we'll name it states. Okay, so we can add items to the states list, just like we do with the vector, so states.pushback, main. We can put a bunch of things in here, and I'm just going to try to put them in not alphabetical order, so we can have the function or the list itself do that for us. Okay, so let's output the items of the list, though this is going to be a little different if you haven't seen an iterator before. We aren't going to be doing much with iterators. There's some extra information about them in your textbook, but at least while we're working with the STL list, this is basically just how we have to iterate through the list. So for list string, iterator, it, starts at basically the beginning of our states list, and it will loop while it is not equal to the end item of the states list, and it will move forward by 1 each time. And we can output the value by using the star operator and outputting it that way. So if I build and run, it will show me the items I put in there in that order. I can also say states.reverse, and then Alaska should be the first one. Or I could say states.sort, comment that out, run. It'll alphabetically sort these, since if you use less than greater than signs with strings, it will automatically return less than or greater than. So for example, like let's just see out. I'm not sure if I can do this with straight literals, but we'll see. Oops, I have to build. Okay, it does not like that with the string literal. And let's just do A is less than B. And so it displays 0 as false. So as long as something is being stored in the list that has the less than greater than operators overloaded, which we'll talk about operator overloading later as a review, as long as there are overloaded relational operators in the object being stored in the list, we can take advantage of its sort function. I'm also going to remove this, so if we wanted it in descending order, we could sort it and then say reverse. We can also use a range-based for loop if we're working with a newer version of C++, so C++ 11 or later. So we could say for auto is introduced in C++ 11, and we will say state in our states list, and we can just output the state. So I'm going to comment this out really quick, and we can just run this, and it should give us the same output. So that's another option, though I will talk about C++ 11 things in a separate location. A queue is a type of restricted access data structure. It stores its contents in a linear order, but you're only able to remove items at the front of the queue and to add new items at the back of the queue. A queue is known as a first in, first out structure, or FIFO, or FIFO. The first item that enters the queue, who sits at the front of the line, is the first one to get removed, just like in a grocery store line. And when a new item is added to the queue, it enters at the end, or otherwise the back. Some handy queue functions are push, to add an item to the back of the queue, pop, to remove an item from the front of the queue, front, which returns the item at the front of the queue without removing it, size to get the size, and empty to get true or false on whether it is empty or not. For more information about the queue, go to the reference page. And now for an example. With a queue, remember to include the queue library, and we're going to just make a queue of commands that our program will iterate through. So let's say a queue, that's too many UEs, a queue of strings, we'll just say it's a string of, a queue of commands, and we're going to push some commands into the queue. So commands.push, make directory, new folder, and so on. So we can do a few of these. These are all just command-lined commands that work with Linux, and I'm just putting some really basic ones in there. So we could say ping Google 5 times, ping Yahoo 3 times. So these are only adding items to the queue. We haven't done anything with them. We'll have to iterate through the queue and pull things out one at a time. So while the queue is not empty, we're going to look at each one. So string command is equal to whatever the frontmost command is. Then we're just going to output it for our own reference. And we're going to use the C++ system command just to run that command. And once we're done, we want to remove that from the top of the, from the front of the queue. So we can build, run. So I will have to show you the example program directory to show you that it made those folders. So we have examples, queue, and it made a new folder and it made a new file as part of these 2 commands here. And then it also pinged Google, then it pinged Yahoo. Oh, okay, those are up there. Sorry, I thought that they didn't show up. So we can write a queue and have these be executed in the order that they were added to the queue. A stack is another type of linear data structure, just like the list, vector, and queue, but like the queue, it also restricts access to the internal data. The main characteristic of a stack is that it is a first in, last out, or last in, first out structure. At any time, you're only able to access one item from the stack, the topmost item. And as items are pushed onto the stack, the older items are on the bottom, and the newer items are at the top. As you remove items from the stack, you pull the newest item that was added to the stack. So the first item on the stack is the very last one to be removed. So let's say for an example of using a stack, we're keeping track of moves in a tic-tac-toe game. Every time a move is made, we would push the game board's current state onto the stack. So we'd put the values of each of the 9 cells into the stack as one object. Then if we want to undo a turn, we can pop the most recent state off the stack and go from state number 3 to state number 2. And the game board reverts to the state prior. Stacks also have push and pop, but push pushes an item to the top of the stack, pop removes an item from the top of the stack, and then the top function returns the item at the top of the stack. There's also size and empty. And you can get more information about the stack from the reference page. Let's look at an example of using a stack. So a queue is first in, first out, and a stack is last in, first out, or first in, last out. And you'll need to include the stack library to use it. We'll just use a stack right now to reverse a string. So let's create a stack of characters, and we're going to iterate through all the letters of whatever the user enters and put in the stack. So we'll basically be putting the first item at the bottom, the second letter at the second to bottom, and so on, and then once we pull it out of the stack, it will be in reverse order. So let's have for unsigned int I is 0, we'll iterate through the length of the text string, and for each letter, let's just show it for reference. Oops. What is letter I? It is whatever it'll be, so we can run this right now as it is and just see that it will show ASDF. And we will add that to the stack. So letters.push this specific letter, and then let's just kind of separate out the parts of the program. So pop off the stack, and we will continually pop items off the stack until it's empty. So letters.empty while the letters stack is not empty. We will look at whatever the topmost item is, so letters.top, and we aren't going to have a line break because it's going to just reverse the string. We can say letters.pop to remove the topmost item, and now when we run it, I can enter something like hello there. So it adds them to the stack in this order, and when it pops it off the stack, it's in reverse order. So hello there, but it removes the topmost item, and then the next, and then the next, and so on until it gets to the bottommost item. When we're using a plain old array, we have a series of elements in order, starting at 0 and going until size -1. So, if we have an array of 7 items, the valid indices are 0 through 6. A value of 0, 1, 2, 3, 4, 5, or 6, which specifies an element's position, is known as an index, but we can also think of it as a key, which helps us locate the value that we want. But with a data structure like a map, our keys don't have to be just integers, and they don't have to be array indices. The key can be any data type, and it can point to a value of any data type as well. For example, think of an employee ID that points to an employee object in a program. Maps are built in a special way so that we can access elements by key, and it will access it quickly. Search algorithm is not required. The functions we'll be using for the STL map are the subscript operator, which will return some element based on the key, the empty function that will return whether it's empty or not, and the size function that will return the amount of elements in the map. There are a lot more functions for the map, and you can look at them at the reference page, but we're not going to get too into it. And now for an example. With our map, once again, remember to include the map library. And we can make a map in this way. So quickly, let's look at when we had the vector, we would put the data type of what the vector is storing inside of these less than greater than signs because it's a template. A map is a key value pair, so we'll need to pass in 2 different data types. So for example, let's say string and int, and we will map an employee name to their ID. So let's say employee name to ID. Then we can add items to the map just by using the subscript operator. So if we have this, we can enter some value in, just like that, and then we can also access items through the key. So let's create a string key, enter an employee name. They'll enter in some key, and if it matches, it will show what the value is, which is an integer. So that employee's ID is, and then we'll output whatever the item is at that key, and that should work. So if we enter something like that's not in there, it's just going to return 0. Well, I don't know if it would be a guaranteed 0. It could just be garbage, potentially, but if I type in Harry, it will give me back the value that we've stored to it. So it can be any set of data type. It could be mapping an integer to a string. We can go in the reverse order, so employee ID to name. And we can say that the employee number 1024 is Harry, and so on. We can say enter an employee ID, int ID, cn the ID. That employee is, and then output the value from the key. So I'm going to go ahead and comment this part out. Let's just say key is 1020 or Ron, and then down here we'll be able to enter something in. So we're skipping over the first cn, enter an employee ID, let's do 512, and then it will display the value. So the value is what the item is storing, and the key is what goes in the subscript operator, and so that's a simple way that we can use maps, and we'll learn to do these more later on in the semester. We will eventually implement each of these structures ourselves to learn how these work. But sometimes it can be handy to view the new concepts from the outside in to begin with. Data structures are all about writing structures, i.e. classes, to store data. Structures need a way to add data, access data, and remove data. We'll be writing lots of add, access, and remove functions this semester.